Well, hi, this is Mathman here, and the last time we took a look at derivatives. We were introducing the idea of finding graphs or drawing graphs using derivatives and how they can be helpful to you in putting together a graph. One thing you should be aware of is that you're going to find that there's a great need to understand factoring in order to be able to use the derivative methodology. And most, if not many, if not most, polynomial functions are very difficult to factor, and there are tricks that can be done. Also, when they give these problems out, like in this book, this is Thomas. This was a classic. Oops, there you go, Thomas. This was a classic in learning calculus. Thomas was actually a professor at MIT. This is an edition that was first published in 1972. It was the fourth edition. And so this was probably the mainstay of calculus in college from the 1960s into the 1970s. And I find it useful, even though I wouldn't recommend it necessarily as a text for learning calculus. It's a little difficult to read because he uses a lot of difficult notation without giving explanation for what they mean. But even here, what they don't tell you in calculus classes is that the functions that they give you to graph using calculus, using derivatives, are functions that you can factor relatively easily. There are far more functions that you can't factor than you can. So that is a real issue with this method. The other thing is that now with many of the tools that we have, it's not as critical. You see, back in the days when this book was published, there were no spreadsheets, there were no calculator, they didn't even have calculators. They didn't have computers that, personal computers with the ability to do the graphing for you. So it was really a necessity that you understand the whole process of being able to use calculus to graph. And in fact, you can actually put together a graph of a function with relatively little information if it's readily factorable. So usually what they don't tell you is that usually the functions that they give you in school to do this, to use calculus to graph, are those functions that you can factor and factor using readily available methods. So anyway, we are going to embark on a couple of examples. Now, one of the things that I've done already is I've created a spreadsheet with some of these functions already worked out, and we're going to go through those so that you can see. I mean, my graphing skills are limited by my artistic skills, which aren't so very good. So it's much better graphically, visually, and I can explain what I did to obtain the different graphs that we're going to take a look at. I'm not going to spend a whole lot of time on this because there's so much more important things than just graphing a function with derivatives. So we're not going to spend that much time on this particular aspect. There are plenty of books that you can find this information about, but we'll go through them, and probably in as much detail as they gave us when I was learning calculus in college. So now we're going to take a look at a function that I created, and this is the function right here, if I've written it down correctly. And basically that looks like a terrible function, and it is. I have to admit, this is an awful function. And it took a lot of time to work out this problem. But what we want to do is we want to factor this function. And the way we do that is there are several ways we can do this. First off, if you look at the coefficients of the first two and the last two terms in the polynomial, if the ratios are the same, then you can factor them. And so in this case, you got 1 and 5, 1 divided by 5. And then over here, the last two, you have minus 20 divided by minus 24. Well, obviously, they're not equal. So we can't use that method. We can't use that approach. So that's out of the question. Now, the other thing is that we can take a look at this last figure, this last term, 24, and factor that. Now, we could use the old-fashioned way, 24, 2, 12, 2, 6, 2, 3, and that gives us a number of different results. That gives us 1 and 24, we got 2 and 12, we have 3 and 8, and we have 4 and 6. And so those encompass the different combinations or factors that can go into making 24. So we use these, and we can use a method called artificial division. And what that entails is taking the coefficients, again, of the polynomials and dividing them in a specific way. 20 minus 24. And I had worked them out that there was a lot, as you can see here. You can see the sheet that I did. There's a lot of work that went into it. I'll just work through those that did work. So remember, the factors are plus or minus. So we got 2, 4, 6, 8, and that's 16. So we have 16 different things that we can look at, and that's a lot of division. So I'm not going to take that kind of time to do it. I'm just going to look at the ones that worked. So here we go. I can tell you right off the bat, neither 1 nor minus 1 worked. So let's take a look at 2. So 2 goes into 1. Well, it doesn't evenly. So 0 times 1 minus 0 is 1. 2 times 1 is 2. 5 minus 2 is 3. 2 times 3 is 6. 2 minus 6 is minus 4. 2 times minus 4 is minus 8. And minus 20 minus 8 is minus 12. 2 times minus 12 is minus 24. And 20 minus 24 minus 24 is 0. So 2 is a factor. Now we can take a look at minus 2. And we can go minus 2, and we got 1, 5, 2, minus 20, minus 24. Again, minus 2 doesn't go into 1, so 1 minus 0 is 1. Minus 2 times 1 is minus 2, so that's 7. That's minus 14. And that is 2 minus 14 is 16. And 16 times minus 2 is minus 32. I believe I got it right. And when you subtract that, that is 12. And minus 20 minus 32 is 12. 2 minus 2 times 12 is minus 24. And again, we get 0. So minus 2 works. So we got 2 terms. How many more can we get? Well, let's try 3. So let's put these guys up here. We got 2 and minus 2 are up there. And now we can go 1, 5, 2, minus 20. You can see how much of a pain in the neck this is, because you gotta, the bigger, the larger, the higher the power, the greater the magnitude of the equation, the more difficult that it becomes, because because it's harder to find the factors. So let's take a look at 3. Again, 3 into 1 doesn't go, so 3 times 1 is 3. That's 2. 5 minus 3 is 2. That's 6. And that's minus 4. And that is minus 12. And this is minus 8. 3 times minus 8 is minus 24, and look at that, we got 0. So 3 goes up here, and we're getting up there. We're moving along. And let's take a look. Let's see, I did more. I think that does it. I think that does it for us. We can do it other ways too, but anyway, we've got a number of the factors. So what do we have? Let's take a look. We've got x plus 3 times x plus 2 and x minus 2, but that's problematic because that only gives us a third order. We don't get x to the fourth out of that, so there must be one more term. And what is that term? Well, we could go through this and we could divide all this through. We can, I believe if we went like this, well, I don't know if it's even worth it. I'm just going to tell you that it's another x plus 2. And so what we have here is x squared minus 4 times x plus 2 and x plus 3. So the zeros of y, and when I say the zeros of y, that's how many times the function crosses the x-axis. Not all functions do cross the x-axis. Be mindful of that. So here we got 1, 2, 4. So, and in our case, we have 4, actually 3, because 2 of them are at the same place. So the zeros are at x equals minus 2 and 2 and minus 3. Minus 3, minus 2, and 2. And let's write that more clearly. So the zeros are at minus 3, minus 2, and plus 2. So that means that gives us some information about the graph already. Okay, so we have y equals x squared minus 4 times x plus 2 times x plus 3. And this y is 0 at x equals minus 3, minus 2, and 2. Okay, so that's how many times that function crosses. Okay, so what do we do? This is a fourth order, okay? This is fourth order. So remember what we had originally was x to the fourth plus 5x to the third plus 2x squared minus 20x minus 24. That's what this expands into. So what we have is we've got okay, so when we have minus 1, minus 2, minus 3, and we got 1, 2, 3, and this is y and x. So when this being the fourth order, anything, any negative, let's say negative 10 to the fourth is going to be 10,000. It's going to be positive. So we're going to have this dominate. The positives dominate. So anything less than minus 3 is going to be above 0. And so everything goes up, probably pretty rapidly. And anything, and here at 2, it crosses at 2. And we know this is minus 3, minus 2, and 2. And these are where our function has zeros. So it goes below there. And we don't know what it does in between these 2 points, but after below minus 3, it's going to be above 0, and above 2, it's going to be above 0, and it's going to go up relatively fast too. So what we're interested in is what's in between. So how do we find that out? We take derivatives. Now, in the last video, remember, we had the derivative formula, the power formula. Y prime equals 4x to the third plus 15x squared plus 4x minus 20. And when we set y prime equals 0, we find the extrema. And the extrema could be either maximums or minimums. So we don't know. And the extrema could be local maximums and local minimums, which means that there are places in the function that either go higher or lower. So let's take a look and see how the screen. Okay. So again, this comes down to factoring, trying to find out what the factors are for that. And so here we see the ratios. 4 over 15 is not equal to 4 over minus 20. So that method is out. We can now take a look at, let's see how I did that. We can take a look at, there we go. We could take a look at the different factors for this. Okay, 20, you got 2, 10, 2, 5. So we got 1 and 20, 2 and 10, 4 and 5. And those, again, could be plus or minus. So let's because I want to save some time, and because it took a long time to work out, we're going to take a look at 2. So 2 into 4 x to the third. We're going to say x plus 2. X plus 2 plus 15 x squared plus 4x minus 20. So this is 4x squared. That's 4x to the third plus 8x squared. That's 7x squared plus 4x. So we go plus 7x. And that's 7x squared plus 14x. And that's minus 10x minus 20. So we go minus 10. And we have minus 10x minus 20, and that's 0. So x plus 2 definitely worked. And now what we've got is this. That this is equal to x plus 2 times 4x squared plus 7x minus 10. Now, we want y prime to be 0. Y prime equals 0. Well, one of them is at x equals minus 2 from that term. And we want this term for x squared plus 7x minus 10 to equals 0. Because when that term is 0, this term, then y prime is 0. And we see here that we got a square, and so we can use the binomial formula. And so we have x equals minus b, okay, 7 over 2a, so that's 8, that's a, plus or minus 1 over 2a, which is 8, times b squared minus 4ac, so 4 times 4 times negative 10. So we have x equals negative 7 over 8 plus or minus 1/8. And this is, okay, that's 16 times 10. That's 160. So 160, 16 times 10 is 160 plus 49. That's 9, 10, 209, square root of 209. So now we have our full factoring. It doesn't turn out to be a nice even number, but we're able to factor it. So let's take a look at this. So x equals minus 7/8 plus square root of 209 over 8, and x equals minus 7/8 minus square root of 209 over 8. Okay, so it's going to leave us with a problem with this, because it's not a nice even number, but it doesn't really matter. Okay, so we have, I think the way I worked it out was we had this equal, it was 2.68 approximately, and this was approximately this. I think this was, we got a. Yeah. I'm sorry. We got it. If we factor out a negative, because x is minus. Okay, so that's going to be that, and that is going to be that, and this is minus 0.9321, and this is minus or plus 2.68. So we got x plus 2.68 times x yes, plus 0.9321, if I am correct. So let's see. Oh, I've got it there. Yeah. All right. Yeah, we can Yeah, we'll just, what we'll do is we'll write it down like this because it's more accurate anyway. Equals x plus 2 times x plus 7 minus square root of 209 over 8 and x minus 7 plus square root of 209 over 8. And those are the factors for this equation. And you can see it's a third order. And these are the zeros, okay? And then now we look at y double prime. And we look at y double prime for the inflection points. And an inflection point is where the curve changes, okay? So right in there is where the curve changed shape. Here, it's cup shape, so y double prime will be positive there. Here it's domed shaped or rounded over, so this would be negative in that area. Okay, and this is where y double prime equals 0. That's where the change takes place. So when you take a look at the zeros of y double prime, and y double prime happens to be 12x squared plus 30x plus 4, okay? And this you can factor out, and that's going to be equal to 0. So we can factor out 4, so we got 3x squared plus 10x plus 1. I believe that works out, equals 0. And so x equals minus 10 over 6 plus or minus 1 over 6 square root of 100 minus 4ac, 4 times 3 times 1. So that's 100 minus 12, which is 88. So that's the square root of 88. 88, we can 4, 2, 2. Okay, so we got 4, 6, and square root of 22. Square root of 22. Here we got equals minus 5 thirds plus or minus 2 thirds square root of 22. So now we have our zeros for y double prime. And those are going to be the inflection points. Now we have all the information that we need. So I think at this point, what we're going to do is we're going to take a look at the spreadsheet I prepared, because it's going to be so much easier to show you graphically what these different derivatives yield for us in terms of information about the graph. Here again, these are the zeros for the function where they cross the x-axis. This is going to find our maximum and minimums. There are going to be 3 of them. We're going to have 3 extrema, and here we've got 2 inflection points. So already we know stuff. So rather than try and draw this all on the board, I have it all prepared in a nice spreadsheet with the graphics already worked out. So let's take a look at that, and we'll hopefully that will be much easier for us to take a look at least from the eyes perspective. Okay, so here we have my spreadsheet, and I've been working on this a little bit. Here you can see this is the function that we were just looking at, okay? And this up here, you will see, and I'm moving it here so that we can see it better. The zeros of y occur at x equals 2, x equals minus 2, and x equals minus 3. I'm sorry, the negative sign was missing. And remember that that mess that I had with the square roots? Well, that turns out to be these factors right here. At y prime, we have a local minimum. At x, we have minima or extrema. Let's call them extrema at this point. Extrema, because we haven't looked at how we can tell whether or not this is a maximum or minimum. But we have extrema at x equals 2, x equals minus 2, and we have extrema at x equals minus 2.68, and so on. That was a square root of 209. Remember, that was a long, that was going to be a very complex number. Nothing is nice and easy. And we also have one at x equals 0.93. Not quite 1, but at 0.93 we have an extrema. And then we have y, let's say y double prime. And remember, that was the whatchamacallit, the one we just worked out. So that was, we can take a look at this. We can find where this is 0 at x equals minus 2.35 and x equals, where's the other 0? Negative 0.141322. So that's what those worked out. Those nice square roots that we had, that's what they worked out to give us. Now, what we do is we take a look. Now, what I did was I plotted the function. This is the x values from minus 4.3 to 2.4. And this is the function, the y values of the function. That's this equation. So if you can see here, you can see that this is a g3 to the 4th. So I plotted that, and basically what you got here, this is the curve. That's the curve we're looking at. So what we do is we take the information that we got, finding the zeros of the function, finding the zeros of the derivative, and finding the zeros of the second derivative. We're able to find out where the function crosses the axis where the local or absolute extrema are, whether it's a minimum or maximum, and we know where the inflection points are. And we have 2 inflection points, 3 extrema, and 4 points, actually 3 points, because x equals 2 repeated itself as a factor. So it only crosses the x-axis 3 times. So now what I did was I created a table and I plugged in these numbers and I looked at whether or not they were what their ultimate signs were going to be. Okay, so at x, and these are x values, at x equals -4, the y is going to be a positive value, and in fact, you could see here it's 24. So when x is -4, the function is positive 24. Like I said, because of it being an even power that dominates over the others, ultimately it's going to override any negative values, and so from -3 and less, you're going to have ever increasing positive values above the x-axis. The same goes for the positive values of 2. So where x equals 2 and above, you're going to find that the value of the function, let's say here 2 is the 0 where we cross the x-axis, and you can see that from 2 on up we got positives, and it's going to stay that way because x to the 4th dominates. So that information helps us. So we know ultimately that this on either side of 0, ultimately this function is going to be yielding positive values. It's what's happening between those places where it crosses, the function crosses the x-axis, that is interesting to us, because we don't know what's happening in between there. So basically, I looked at the specific values that we calculated for y and y prime and double y prime, and I looked at their signs and their values. So where y prime is 0, which happened to be at x equals -2.68, that's going to be an extrema. The same where we have x equals -2. We have an extrema, as well as intersecting the x-axis. And that one's kind of interesting because that happens to be a, just for your information, that happens to be a our local maxima, as you can see here, local maxima. And it happens to be at the x-axis on 0. So it doesn't cross exactly, but it intersects the x-axis, as well as being an extrema for us. Now finally, our last value for y prime that caused y prime to be 0 was when x was 0.9321. And we see that's where the function again crosses the x-axis, and or not crosses the x-axis, but that's where we're going to find an extrema. In fact, the actual value for y there is -36. And when we look at the other 2 points where we have extrema, where y prime is 0, the values of y are -0.69, 0, and minus 36. So this is our absolute minimum. Our function doesn't get any lower than this at that point. So at point 93210, we find our function has its absolute minimum of minus 36.1. Now, what we are looking at, how do we know that these things are extrema, whether they're minimum or maximums? We look at the second derivative. Now, around where y is 0 at the extrema, we look at the sign of y double prime, and you can see they're positive. So around this value here of x equals minus 2.68 minus 2.68, these values are all positive, which means it's cup-shaped. And we'll take a look at that at minus 0.268. Now, this is our inflection point right there. Minus 2.68 is right there. I got that red line intersecting the bottom of the curve right at where we have the local minima. And this is the value where we calculated, what was it, minus 0.69. And then the curve, you can see the curve is cup-shaped because from minus 2.68 to minus 2.35, the curve values are positive, and that means it's cup-shaped, or you can think of it as being able to hold water. But at the inflection point, at 0.236, I calculated, at this point where the arrow points, that's the inflection point. You can see very carefully that's where the curve changes at x equals minus 2.36, and it's dome-shaped. Okay, so water runs off that. It wouldn't hold water. So it's not a cup shape, it's a dome shape. And it's dome shaped all the way to this point here where we have the value minus 0.143, where the change of the shape of the curve again changes to become cup shaped. And so when this is positive and positive on either side of your minima, and that means you're going down and you're going back up again, and this cup shape means that you've reached a minimum and you're going back up again. So having positives on your second derivative on either side of your extrema tells you that you have a minimum. Over here, we have negative second derivatives at the point x equals minus 2, and that's our local maximum of the function, because y equals 0 at that point. So at x equals minus 2, not only do we intersect the x-axis, it is also our local maxima, because we have a negative on either side of our second derivative. So the second derivative at minus 2.1 or minus 2.2 is going to be negative, and over here at minus 1.9, it's negative. So the negatives on either side of that extrema says that extrema is a maximum. And finally, looking at our last extrema, that's this point here, minus 2.68. We look on either side of 2.68 minus 2.68, and the second derivative is positive on either side. And we can take a look at that table again, and you could see that on 2.68, on either side, here at minus 2.58 and minus 2.78, you could see that the second derivative is positive. So that's going to be a local minimum. This extrema at x equals minus 2, the y value is 0, as well as the y prime, which tells us it's an extrema. But the fact that it's negative on either side at minus 2.1 and minus 1.9, we see that the second derivative is negative and negative, and so it's dome-shaped. It's not going to hold water. It's not cup-shaped. So that means we have a local maximum. And then again, we have an inflection point at this value on the x-axis, minus 0.14132, which shows that the shape of the second derivative has again become positive or cup-shaped. And that means at our other extrema, our last extrema, that occurs at x equals 0.932, when you look at that extrema, you see that the second derivatives are positive on either side of that value, and that means that that's a minimum. And the fact that this y value is smaller than the other minimum says that this is the absolute minimum of the function. So that's how this data, this information, before we even could put pen to paper, if we look at this table and just look at the signs and where the different derivatives and values of the function are 0, gives us enough information for us to understand what the graph is going to look like. And so we don't have to spend a lot of time plotting points and hoping that we've plotted them close enough to not miss something in the curve. So that's the utility of this. Again, I can't stress the fact that most functions are not going to be this easy, and this was not an easy function because it was a higher power. The higher the powers you go, the more difficult it's going to be, because factoring becomes more difficult. So that's why in a calculus class they limit the problems to much simpler problems. Now, out of Thomas, the book I showed you, which was the standard out of MIT for most colleges in the United States during the 70s and 60s, even the 50s, they had a couple of problems in there that I thought were interesting, and especially this one. And I found how interesting, how fabricated they were because because of the problem of finding a polynomial that will actually factor. Here is the equation that we're given right here. Y equals x to the fourth minus 2x squared plus 2. And it looks simpler. So it really isn't. There's a little trick to this one. None of the factoring tricks that I showed you worked on this particular problem. So what I did was, noticing that we had factors of, or powers of x that were multiples of one another. For example, x to the fourth is a multiple of x squared. You can use a little trick. You can use a substitution where u equals x squared. And then when you plug that back in, you have a second order equation that you're solving. It's just your binomial equation. So you end up with u squared minus 2u plus 2. And what that does is it gives you u equals 1 plus I. When you apply the binomial equation, x equals minus b over 2a plus or minus 1 over 2a times the square root of b squared minus 4ac. That gives you the solution to a second order or squared equation. You end up, in this case, having a negative square root. And so that tells you something very interesting. That tells you that this function never crosses the x-axis because you have the imaginary number in the roots of the equation. And when you plug that solution back in to the function, this is what you get. You end up with u minus 1 plus I times u minus 1 minus I. And that, when you plug back in that substitution where u equals x squared, you find that you can then further factor, and you end up with this great big monstrosity, and none of it crosses the x-axis because there are no zeros to this particular function. So that was something that they deliberately did to throw the students off because it does involve the imaginary numbers, which is the square root of minus 1. However, when we take the derivative of this function, we end up with y prime equals 4x to the third minus 4x. Now, that one is factorable. And in fact, it has 3 values at which it's 0. So that means this function has 3 extrema. Whether they're maximum or minimums, we don't know yet, but we do know that we have 3 extrema. Okay, again, this function, like other functions, being a x to the fourth, when you go far to the negative side, it's going to be a positive. In fact, this never does get into the negative realm for y. And far to the right on the x-axis in the positive x domain, you will find that this will be also positive for all values. But at certain points, we've got some interesting behavior, and that is because we found we have 3 extrema, maximum and minimums at these points. In fact, x equals 0, x equals minus 1, and x equals 1. So at least they made that nice and easy for us. Now, when we get down to the second derivatives, we have yet a simpler equation. Y double prime, the second derivative, is 12x squared minus 4. You can factor out 4, and you got 3x squared minus 1. And so your zeros are at 2 points. for this equation. So you have two zeros or two inflection points for this function. So you got 3 extrema and 2 inflection points, and that makes sense. We have an inflection point at x equals negative square root of 1/3, and another 0 or inflection point at positive square root of 1/3. So now we put that information into the table like we did, and I calculated, like you see here, I plotted between -2 and +2, and you can see that this has got a lot of symmetry to it. At -2, the function yields the result of 10. At +2, it also yields 10. So it's a very symmetrical function, and the symmetry is around the y-axis at x equals 0. So our 3 extrema are at x equals -1, x equals 0, and x equals 1. So that's where we're going to either have maximums or minimums. And here we're looking at the values where y double prime is 0, and this is not correct. This is right there, and what I had done was I kind of screwed up. Oops. I don't know why. Oh, what am I doing here? Okay, now this is -1. That's going to be positive, and right there. Why is it doing this? This is positive, and this is also positive. Okay, so now let's look around our extrema. We have, okay, we have a positive on this. Let's see, at 0.9. Okay. At, let's see. That's positive. Okay, so this is positive. So that, darn, why is this, why am I having so much trouble with that? And here, this is the other extrema. Okay, these are the inflection points. This other extrema is, okay, equals 12 times this squared minus 4 times this. And that's positive. Okay, so that is positive. Sorry about that. I just want to make sure that this table is correct. And we do. So basically what this says, now around our extrema, this is our extrema at x equals 1. our second derivative is positive, so that's cup-shaped. Around this extrema, on either side of that extrema, it's negative, so it's dome shape. And around this extrema, again, we got positives, and it's cup-shaped. So that means this is a minimum. This is a local minimum, and the y value happens to be 1. Over here, we have another local minima, and the value again is 1. Okay, so those are going to be the absolute extrema for the lowest value of that function. So the smallest that function gets is 1. And it happens at both sides, at x equals -1 and x equals +1. These are minima because the second derivative is positive on either side of that -1 value. And the same goes with the +1. The second derivative is positive on either side of x equals +1. And so we know that both of those are cup-shaped, they hold water, and so they're local minima. Now, this one, where we have a local extrema, we have negatives on either side of that extrema, which means it's a local maximum. So in between those minimums, this is a maximum. So the curve changes shape in between 0 and -1 and 0 and 1. In fact, that's where our inflection point is at x equals 0.577 and at x equals -0.577. That is where our inflection points take place. And that's what gives us this pretty cool curve. This value here is 2. As you can see on the y-axis, this is 2. This is x equals 0. You got -1, +1. You have the local minimum. They're they're both the absolute minimum for this function. They both yield exactly the same value, though, of 1. This function never crosses the x-axis, so there are no zeros for the function. And the orange circles are where the inflection points are at -0.577, almost -0.6, and at +0.577. So that gives you a pretty interesting graph, and you can see how it's plotted here when I added some points. It's much prettier in Excel than it is with me hand drawing it. But that is how you find your local extrema. That's how you plot using derivatives to understand what the behavior is of the function is when you don't have anything like a computer or a spreadsheet or anything like that. And when you want to be absolutely sure of your graph, this is the information that you need in order to be assured that you've got the right graph for your function. Now, I threw in a couple more functions in here, just 2 more to mix it up a little bit. You can recognize this. This is your cosine function. This is a trigonometric function. And I plotted this between for one cycle or one period. So from the angles or the angle, the x-axis are the angles, with the degrees running from 0 to 360 at 5-degree intervals. And so I have the function y and the derivative of cosine function y prime, and double y, the second derivative of the cosine function. And as you can see here, the cosine function, its derivative is the negative sine function, and then the second derivative is the negative cosine function. So when we look at the zeros for the cosine function, for the one period or the one cycle, the zeros occur at 2 points. The graph crosses at x equals 90 degrees and 270 degrees. That's where the cosine function is 0. The derivative minus sine x is 0 at x equals 0 and at x equals 180 degrees. Those are where your extrema are going to be. And then y double prime is 0 at 90 degrees and 270 degrees again, and that's where your inflection point is going to be. Now I set up a table where I plotted the x-axis in terms of degrees, where the zeros are for cosine function, where the zeros are for the derivative minus sine, and the negatives and positives for the second derivative, which is the negative cosine. And we can see here that with this plot, all the way down here to 90 degrees, from 0 to 90 degrees, our second derivative is going to be negative, and therefore it's dome-shaped. But at 90 degrees, where it crosses the x-axis into the negative realm, you can see that the function becomes cup-shaped, and so that holds water. That means at the extrema, where the sine function is 0 at 180 degrees, is a minimum on this interval from 0 to 360 degrees. This is our absolute minimum, and that's going to be a value of 1. The inflection points are at 90 and 270 degrees. And then our maximums are of this function on this interval occur, again, where the sine function is 0, at x equals 0 and x equals 360 degrees. And the maximums are here at those points at a value of 1. Positive 1. And we know that they're maximums because if we plot it on both sides, the second derivative, the values would be negative on both sides of this. So that means this is a peak, and that would also be a peak. These are negative. You can see it's dome-shaped versus cup-shaped here. This is where the curves change shape, the inflection points. And so this is the graph of a cosine function. And you can see how all this information is contained in this table that we created out of just taking the functions and their derivatives and looking for the zeros. And it gives us a lot of information that allows us to be able to graph with a surety. In fact, without a whole lot of prior knowledge. And I think at this point I may want to quit. There was one more function I really did want to look at, and that was the tangent function. That yields a very, very interesting graph, because when you look at the tangent and you take its derivatives, they're not simple. The tangent function itself is a combination of two functions. It's the sine function divided by the cosine. And so you're going to have points where the cosine function is 0. That means the tangent function is not defined at that point. And that happens to be at 90 degrees and 270 degrees. We simply, you can't have a division by 0. So what we have at those points, 90 right there and 270, these act asymptotically as limits for the function. On this side, from 0 to 90 degrees, you'll see that the second derivative is always positive. It's cupped. Therefore, it's curving upwards. And because the derivative has no zeros, the derivative has no zeros, the derivative is always positive, except where it's undefined at 90 and 270. And so y prime is always going to be increasing on the interval that we define, 0 to 360. And at those two breaks where the cosine function is not defined, you'll see that they go either to negative infinity or positive infinity. There's no maximum to this function. There are no extrema. But we can get useful information on plotting it by looking at how it's shaped using the second derivatives and looking at where that is 0 and looking at where those inflection points are and the curve. And in fact, on this curve, there's only one inflection point, and that's in the middle at 180 degrees. Now, if we had taken this out to 2 cycles, what we would have here is you would take this half and put it over here, and that would go up like this. You would have repeating function like this, graph, over and over again with these asymptotic points where the function's not defined. And but I only took it one cycle, but the other half of this would look like this. And the other half of this would look like that over here. And you could see that both, when they're put together, yield this. And so this point would then be an inflection point. And in fact, that is where the second derivative is indeed 0. But the thing I thought was interesting about this is when we go back to the data and the data table, it's looking at what the derivatives are. Because the derivative of the tangent function is the square of the secant, and then the derivative of the square of the secant, which is also the second derivative of the tangent function, is 2 times the tangent function times the square of the secant. So I just thought that was pretty cool. I left some notes here. You can stop and read these if you have the ability. I'm not quite sure how well these will show up on the screen. I think you'll be able to read it. I tried to use a large enough font. I used 18-point font to try and make this as readable as possible. And you can stop this at any time and read it and see, the information that I have put in here that is useful to understanding how we graph. And here I made some notes that this graph is over one period, 0 to 360. If the range was extended over several periods, these zeros, this one and that one, would be inflection points. And no zeros for the second derivative means there are no extrema. And the function is undefined at 90 and 270 degrees, which are asymptotic limits, which affect the functions. They can never be at 90 degrees. The closer you get, the larger it's like trying to divide by 0. The smaller the denominator is, the larger your ratio is going to be. And in fact, as you approach 0, the ratio will approach infinity. So that's what we're looking at here. So anyway, I hope this has been informational, helpful. Again, plotting curves it was a lot more useful to mathematicians back in the 19th and 20th centuries that didn't have the abilities of plugging in numbers in a spreadsheet and looking at how they come out. They were able to draw their graphs using this information from the derivatives and the second derivatives, looking at the zeros and the whether or not they were positive or negative. And so that really helps in understanding the behavior or the characteristics of the functions. So with that, I'm going to call it quits, and I thank you for your patience. This has been a very packed, dense video with a lot of information, but I think the hopefully the points came across well enough. If you need any help in understanding the concepts that were presented in this video, your comments would be very much appreciated, and I would do my best at trying to answer any questions, or if you have some point that you want clarified, I would be glad to do my best at clarifying whatever you may be fuzzy about. So anyway, until next time, we're going to take a look at derivatives again, and we're going to look at some of the other factors, other features of derivatives that are actually more interesting because they relate to physical phenomena, physical behavior. And so until then, this is Mathman, wishing you all the best.
But while most of these cases were reported within hours,
there was another case in Wales which took far longer to reach the police.